Good. So, how many of you were actually here last year when I did the first Jam talk? Okay, not so many. Interesting. Okay, this might be a bit of a jump in the deep end for you. Apologies for that. I do have some pictures that I didn't have last time, so hopefully they will provide good material for those that were here last time and will help make what I was talking about, what I will be talking about later on in the presentation, a bit more comprehensible for those who were not here last time. So Jam, who's heard of Jam? Not that many, okay. Jam stands for Join, Accumulate, Machine, and it's a project I've been working on now for 2 years. And it's expected to be the forthcoming technical upgrade for Polkadot. And it takes elements of Polkadot, particularly how Polkadot sort of works, some of the technologies behind Polkadot, but resets them in a more general and accessible framework, closer to what Ethereum L1 at least provides. Here's a picture. This picture demonstrates, or it aims to depict, the ideal situation. The ideal situation being very simple general processes that execute in some shared state and therefore are atomically composable, that basically are like actors. They don't need to think about block gas limits or transactions or anything like this. They just execute. They're just like a continuous process. Basically, this is what your Linux or Windows or Darwin/OS X, OS 10 operating system provides for your software, right? Now, blockchain software, it doesn't get this. Instead, at least if it's similar to Ethereum, and almost all of them are, it gets something much more like this. Basically, a sort of shared environment, shared state space that allows for atomic composition, but a lot of the time it doesn't really do very much because it's busy doing other things like broadcasting and coming to consensus over what it is, what state the machine is currently in. And also, these things tend to be, at best, sort of limited to the number of CPU threads, and at worst, as in Ethereum L1's case, just a single thread. So when it wants to switch between the different processes or smart contracts, it has to stop doing the previous one. Now you'll also notice that unlike this, where the arrows go all the way from the top to the bottom, and if you can imagine a sort of infinite vertical axis, they would go all the way from minus infinity to all the way to plus infinity. Here they are very much limited, right? They start and they stop. They are finite. And actually, it turns out that if you only do one thing at once, you can just sort of simplify it to a single arrow with a slightly more complex state transition function and storage. Now, I'm going to compare that to Polkadot, in case you don't know anything about Polkadot's architecture. So Polkadot also has everything sort of sitting in quote unquote the same sort of state space, but they're prevented from talking to each other. That's why there's big vertical lines down there. And in fact, when they talk to each other, they do so by sending asynchronous messages that take, say, about a block or two to be delivered. And that's the tangled mess of dotted lines that try to draw sort of asynchronous messaging between the arrows. Now, the arrows are bigger, they're longer, they're more time doing stuff, but they are still very much finite in length. There is a start and a stop to them. This means they must pack their state up, store it, because their execution environment is going to get reset in the next block or whatever. Jam changes this paradigm substantially. This is an artist's impression, I'm the artist, on what precisely Jam is sort of doing or how it's architected. So on the left there is our data lake. This stores lots and lots and lots of data. 1.6 petabytes is our estimation. On the right-hand side is our main sort of state machine. And then this is the thing that has all of the different sort of smart contracts or processes that are operating. Now you'll notice that they also only operate one at a time. In the middle is the interesting bit. These are what we call the cores. And these are stateless processing units. And whenever data comes in to a JAM machine, it goes through the cores before it gets into the main stateful system. So we call this the cores part, the sort of stateless bit, and the one on the right, the stateful bit. Now the one on the right looks more or less like Ethereum. But the one in the middle, not so much. The one in the middle is doing lots and lots of computation. Now you'll notice also that they're both they're blue, like Ethereum, whereas in my ideal picture, red. What does the red mean? It means that our concept of memory, our concept of a stack, registers, these are all normal. Normal for, say, normal software, x86, ARM64, that kind of thing. This is very different to the instruction set architecture that blockchain systems typically utilize, in Ethereum's case, the EVM. So far, you got the idea, all right, well, there's some processing, some sort of pre-processing between the input and the output. Now, also in the middle, it can read from and write into the data lake, making it an effective storage solution. Now, it's only actually kind of, it doesn't quite do the same thing as the stateful storage system on the right there. It does something a little bit different. Effectively, it's sort of like a library or almost like a DHT. It allows you to put data into the storage solution and get a handle out, but it doesn't provide the sort of name spacing or the arbitrary names that you would get when you write, say, a storage key. Write to a storage key, put a value in, key value, right? It's more of a DHT than a sort of key value storage system. Anyway, more on that in a little bit later. For now, just sort of ruminate on how there's a lot more parallelized computation going on here. Each of these sort of cores, each of these sort of computation threads, they're stateless, they're definite, so they're limited in how much they execute by, there is this idea of affinity, which is basically that gray line that goes between the two arrows. When the arrow stops and then later begins again, there is some favoritism over which sort of arrow you are and whether you are continuing, depending on what data you've put out and want to get in again, on the same arrow as before. Again, I'm going to elucidate on that in a second. Okay, so that's the pictorial sort of description. This is the more technical description. So there is a pipeline, a sort of computation pipeline that JAM implies. It's 3 stages: authorize, refine, and accumulate. And you can basically imagine the 3 stages, the different combinations, depending on whether you're in a stateless environment or a stateful environment, and depending on whether you're running the authorizer code or the service code. Now, the authorizer code is just a little bit of code that just helps JAM understand whether this work has been paid for. All right? It's a little bit similar to one of the more recent EIPs that aims to sort of aims to get rid of the idea of like a signatory that pays for the gas for a transaction and instead allows for other entities to pay for the gas, presumably on some sort of algorithmic basis. JAM has this sort of built into the protocol. So the first thing that's executed is this algorithmic sort of either this work is allowed to be done, it's been paid for in some way, or it's not, throw it out and stop before you've done anything substantial. The next step is refine. Refine is the service code. So this is now doing useful work that we've paid for, work that we want done. But it's in the stateless environment, and that comes with some limitations that I'm going to describe in a second. Finally, the output of refine goes into accumulate, and now we're in a stateful environment, and we can do things that we would generally expect to be able to do within a blockchain. They're both the service code. So, I'm going to quickly go over the sort of different elements as they pass through Jam. So we have the concept of an item. An item is basically a transaction. You can think of it as a transaction. It's a transaction minus the signature. We don't force our external data to be kind of signed from anyone in the same way that we would do in a transaction-oriented system like Ethereum. Items are associated with a service. Well, a service is a bit like a smart contract. You can think of a service as a smart contract. So when you send a transaction into a smart contract, in the Jam sort of way of thinking, well, the smart contract is more like a service. And when you send an item into a service, right, makes the service code execute, just like a transaction makes some smart contract code execute. Now, a package is where things get a little bit complicated or a little bit different. A package is a bunch of items. So we kind of batch up our quote-unquote transactions into a package or a work package. And this is where we include some data, which we call here a token, which is a bit like, or at least it's the substitute or the replacement for what in Ethereum your transactions would have a signature. Well, it's a replacement for that signature, right? It, in some sense, helps prove that this work, these transactions, these items, have been paid for. Now, after the package gets into the system and we authorize it, we do the refinement, right? We do all this computation, this hardcore middle of the diagram computation. We get some data that's the output. We call that output digest. That's also associated with a service, whichever service generated it. And that digest makes its way into accumulate. So these are the kind of transformations that happen. In the authorized stage, we have a work package. We get a trace from the authorization, actually, that's what it's called. And then in the refined stage, we can combine that with the items, with an item, and get a digest. And then in the join stage, we take all of these digests and traces, and we aggregate them by the service. In this case, I'm showing the red service aggregating. And then in accumulate, we pass these aggregated digests into the service code and execute it statefully. That's basically what this slide says. Now, there's, as I said, two different parts of this, refine and accumulate. I don't want to go too deeply into this because I'm going to give you an example in a second. But basically, refine is something that's done on a single piece of information that we're introducing into the system, a single quote-unquote transaction. And it can do a few things. We have the concept of kind of what we call pre-image lookups, right? So you can pass a hash and get a pre-image. Now you can only do this if it's been stored in a fairly limited or comparatively costly data storage that is available in the stateful or stateless environment. And we can also invoke virtual machines. I'm going to go into this in a second. Items have a maximum of 12 megabytes of data that they can draw in from the world, and they may place up to 12 megabytes of data into our data lake, our data storage solution. And they may yield 48 kilobytes for accumulate. Into accumulate, well, these things take those 48 kilobytes, bits of information, up to 48, and basically do some stuff on the system state, right? Do what you would normally expect sort of smart contracts to be doing. Altering people's balances potentially, but generally doing something in a synchronous, stateful way. Good, right, I'm going to go back to that in a second and give you some examples. The only other thing I want to cover at the moment is the security underlying Jam. It's all very well kind of saying, wow, we got all of this computation power. We can do all of this work. But what's actually backing it up? If it's not secure, then it kind of doesn't really matter how much work we're doing because it might be wrong. So jam security is based on a system called ELVES. ELVES was designed, the Web3 Foundation research team, for securing Polkadot. Now, ELVES is a crypto-economic means of securing, of basically scaling correctness. That's what you can call this sort of thing, right? Scaling correctness. We, through having all nodes execute, or all validator nodes, and basically all full nodes, execute the block, we know, or we have good reason to believe, that the ramifications of the block, which is also recorded in the block header, are correct. And then like clients, on that basis, don't need to be concerned too much about what computation has actually happened. They can just look at the commitment, the sort of ramifications, the commitment to the ramifications, and sort of believe the world based purely on that, and presumably some sort of finality proof. Now, this is all very well, but if you force all of the validators and all full nodes to compute everything and have all of the data available in order to be able to compute everything that requires, it doesn't scale, turns out. And what we're really doing is providing this correctness. This is the magic that we want to get. There are, roughly speaking, two ways of scaling this correctness, scaling the magic that blockchains do. Broadly speaking, zero-knowledge sort of proof mechanisms, snarks and starks and so on, and crypto-economic mechanisms. ELVES falls into the latter. ELVES is very much a crypto-economic mechanism. So, how does it work? Well, unsurprisingly, this being a computer science field, we use divide and conquer. Rather than have all validators check the correctness of all of the work that's been going on, which doesn't scale, we split it up, and we have, as it turns out, of the 1,023 validators, only 3 of them, in some cases only 2 of them, actually, sort of initially at least, generate the ramifications, right? Sign off on the ramifications. That's not very many. That's not correct. That's not that. We have no good reason, I should say, to believe that that's correct. However, we make these validators, because they sign on them, these are staked validators. And we say, well, look, if you've signed that this report, this set of ramifications, are correct, and they turn out not to be correct, then you will be punished. Yeah? And punishment in this case can be a big deal, right? Can be a big chunk of their stake. Now, we need a way of convincing potentially malicious guarantors that they will be found out if they cheat. We have to ensure that their expected eventual gain will be negative, that they will lose their money. How do we do this? Well, firstly, we have these guarantors, these validators who are issuing guarantees, which is all of them, assuming all the cores are active. We have them put all of the data that's required to statelessly check their report, check their work, right? Audit their work. We put this data into a bundle. We bundle it up. And we put it into a decentralized data distributed availability system, secure DA system. Once data goes into the DA, we have credible confidence that it will be ready for any of the validators to fetch, right? And we do this through erasure coding. So we do a rate 3 erasure code across all validators. Now, once we know that this erasure coding is complete for any particular report/bundle, then we can begin auditing. What happens in auditing? Well, validators, they self-select as auditors for one or more, usually more, work bundles. Right? They check some other validators' work. This is done secretly by a VRF. And when they decide that they're on the hook to check some work, they broadcast, they make an announcement to all of the validators. I'm going to check this work, and here's the proof, the VRF proof, that I should be checking it. After auditing it, presuming it's positive, I mean, it doesn't really matter, positive or negative either way, they broadcast the judgment. Usually it's going to be a positive judgment. If it's a negative judgment, someone's going to get punished. Either the original guarantors, because they made an incorrect guarantee, or the auditor, because they made an incorrect judgment. But either way, the world can stop because someone is going to get slashed. So announcements, what happens if a validator gets DOSed just for a few seconds, but enough that once we see that they're actually doing this auditing, they can't give their negative judgment? What happens if that DOS attack happens? That's a major attack vector for this. Well, basically, this is why we do the announcements first. If you see an announcement and you don't see a later judgment, you have to assume that the validator is being attacked. The auditor, I should say, is being attacked, and that the judgment may very well be negative. And therefore, if you see this behavior, you do more rounds on that particular work package, work bundle report. The one that the auditor was, that we presume is sort of missing in action, was meant to be judging. Of course, if you see a negative judgment, everyone immediately audits, because we definitely know someone is going to get slashed. And there are a few additional sort of details that I'm not covering for some of the edge cases, but basically this has been demonstrated in a paper released at an international sort of mathematicians conference, that it provides effectively the same security as the regular everybody verifies everything with, the 2/3 or 50% or whatever finality. It's of the same order of magnitude. Let's compare this to ZK approach to scaling. So if you're not familiar, ZK basically uses some pretty exotic crypto, snarks and starks most of the time, in order to scale correctness of a base layer, right? The base layer is only required to verify a proof, which is generally a lot easier than generating the proof. It may not be a lot easier than executing the proof, but we assume for now that everyone is going to have to do this, which means we would presume it's easier than everyone executing the underlying computation. So we package it up into these proofs, and we just have everyone check the proof rather than everyone do the computation. Now, it turns out that this is a lot more expensive using present technology, like cutting edge, what we have today, what is available in products today. It also adds substantial latency and centralization. Now, we did some substantial research on this, of course, before deciding, coming to this conclusion. And we used ZK Sync Era and the Polygon ZK VM as a means of comparison, and found basically that with these technologies you could do about 44,000 EVM gas per US dollar. So every US dollar got you about that amount of gas. Now, this doesn't take into account data storage costs, because you'll generally need to, like, if these proofs are going to be sort of useful for later participants in your system, you're probably going to want to store the data that allowed you to create the proofs somewhere as well. Otherwise, it's going to be hard, one presumes, to make any more proofs if you're not the prover themselves. It also doesn't account for the proof verification, which again we would presume is probably non-zero, given it's going to be on some potentially quite busy base chain that has to actually come up with its own ground zero security, right? So it's going to need its stakers and all the rest of it. It introduces a fair amount of time to inclusion. Now this is at the moment, using existing technologies, somewhere between 400, like 190, 400 seconds, depending on the technology you use. This could go down, probably if cost goes up substantially. It's not clear it will ever go down that far. And then, of course, you've got the regular finality system, which on Ethereum is going to be somewhere between immediate, more or less, like one block, or about 14 minutes worth of blocks. And this all assumes that the L1 gas fees are actually sustainable. Well, they might be, they might not be. I think they were for a while. They're not necessarily going to be sustainable indefinitely. On the Polkadot, well, the Jam side, the Elves side, I should say, we've got a few assumptions. So this puts a very particular security bound on the amount that you can expect guarantors to lose, depending on how much they try to screw the sort of system with incorrect computation. I've given some example numbers here, but this is linearly scaling, right? So if you want 10 billion staked, and therefore potentially, increase the security factor by 10, then you can just reduce the amount of gas per US dollar by 10, by a factor of 10. I think these are like fairly reasonable bounds for basically all transactions that we're likely to want to do. And as you can see, the factor is substantial, right? It's a little over 2 million, not accounting for the extra costs over here. And the latency is lower. The thing that we haven't done much quantification of is the centralization aspect. This is real, and in fact, it's real enough that the ZK Sync guys have sort of added a number of mechanisms to try to manage the fact that centralization and therefore sort of censorship and so on it can be an issue. As far as we know, the Polygon guys haven't done that yet. But yes, it's an issue, and we have to have sort of clever ways of working around it. Okay, good. So that's why we don't use ZK as a computation scaling solution. Now, it might not matter that your gas, that you're paying $1 per, whatever, 44,000 gas. If your transactions are worth thousands or millions. But if we want to sort of bring Web3, the Web3 concept, decentralized computation, decentralized services, to quote unquote the masses, the mainstream, then we're going to have to reduce this cost quite a lot. Yeah, this isn't going to work. This cost. It needs to be roughly similar to the cost of a database transaction on a Web2 system, and it's a lot less than that. Much more akin to that, and probably still some orders of magnitude beyond that. Okay, good. Right, now, CoreVM. CoreVM is one of the first services that we've made on Jam. I'm calling it Jam's first operating system. Don't know if that's really true or not, but anyway, think of it like that, I suppose. And it has a number of tools associated with it. One of them is the testnet tool. Because Jam is like, you can't really just have one Jam node, because you need a few Jam nodes to do this guaranteeing sort of availability auditing thing. So the testnet, as it stands, spins up a 6-node, 2-core local network. We call it a tiny jam network. And I've got one running on this laptop here that I'm going to plug in a second. That's all it does. It just boils it down to a single sort of CLI invocation. We have a tool called jam top. You know what top is? It's like a Unix tool, lets you see what's going on your computer. Yeah. So if you get all of the processes, and then you get like a bunch of things, so that, you know, what the process is doing, how much CPU it's using, all the rest of it. It looks a bit like this, actually. But this isn't top, this is jam top. And this treats jam like the computer that it is, and gives you the sort of top view of what's going on your jam computer. Now, at the moment, as I said, this is using the 2-core sort of tiny version of jam, which is why there's only 2 orange sort of rows on that graph up there at the top right. If this were running on a real jam, full-scale jam version, there would have to be 341 orange rows, which obviously wouldn't fit onto most terminal windows. So I'll have to come up with a better way of visualizing what's going on the course. But other than that, you can basically treat this as like a CPU monitor, right? So it's just telling you how much work's being done. Yeah? If there's no orange for 0 or for 1, then it means that at the moment that core is idle. If there's a block, then depending on how high the block is, that's how much work's being done on the core right now. And the time scale is in blocks of 6 seconds. That's our block time. The green A is the accumulate processor unit, which is this sort of stateful one. And then the X is for transfers, which are sort of the extra bit that run when services want to talk to each other. What else have we got? Jam-T. This is a general CLI tool for creating and interacting with services, right? Basically, it lets us create new quote-unquote processes on our jam computer. One type of process that we can create is a virtual machine, a sort of, well, something I'm going to go into in a second, but what CoreVM gives us. And we use Jam-T to basically use Jam, right? We kind of interact with Jam through it. All right, so architecting services. I'm going to go through this quite fast now. Now, when you architect a service, I've been banging on about this idea of like refine and accumulate. 2 stages. One of them sits in the stateless bit. One of them sits in the stateful bit. Refine, accumulate. How do you know what bits of logic to put in refine versus what bits of logic to put in accumulate? Well, okay, both refine and accumulate, correctness is guaranteed, right? The system guarantees that it will execute correctly. You don't have to be worried about security. In both of them, the code that's running is guaranteed. You guarantee to be the same code that runs in refine for any particular bit of work, transaction, and in accumulate. There'll be the same code that's running, even if the code gets upgraded, which, yes, you are allowed to do. That's where the similarities end. In refine, the actual storage of a service is not inspectable because it's running basically sort of asynchronously. It doesn't know what the storage is. Hasn't been decided yet. Now, the inputs to refine are provided by the builder, if you like, the person who is crafting the transaction. And there is no good reason to believe that the builder is a benevolent force in all of this. Now, the builder has to create some sort of authorization because they have to prove that the work has been paid for. Maybe they paid for it, maybe someone else paid for it, but nonetheless, they have to prove that it's paid for. And so the authorizer can be made, depending on its logic, to tell you, to identify who the builder is. Now, some authorizers maybe don't bother doing anything. Others maybe require the builder to be some sort of validator or collator or something. But nonetheless, regardless of that, we can't really trust the builder, which means we can't really trust the inputs. What are we to do? Let's move to accumulate. Well, in accumulate, the correctness is guaranteed, the code is guaranteed, as I mentioned. Now, the input is also guaranteed to be whatever has come out of refine, right? We're guaranteed that. No malevolent force can alter the input from anything that other than what has run through the refine code path. Furthermore, the storage of the service is inspectable, just as you would expect if you were running something on a regular smart contract platform like Ethereum. So what do we do? Well, the builder oracleizes, right? They tell the refine logic, hey, actually, this is the state of the service at the moment. Now, the refine logic has no great reason to trust the builder. So what do? Well, they suppose it's correct, and then they pass those suppositions as commitments, little short things, into accumulate, and let accumulate verify it based on the ground truth of the service's state, or for that matter, whatever else is on the chain. This is totally viable. So let's move on to the concept of the storage. We have two different storage systems. We have the data lake and the service storage system. How do we manage these? Well, what are the characteristics? The data lake can be accessed in refine. It can't be accessed in accumulate. The data lake doesn't have a nameable means of placing data in it. When you place data in the data lake, you get given a cryptographic, universally unique identifier for that data. But you can't choose it, which means when you put it in, you know how to get it back out, and you have some data that you can advertise it with, but there's no way that anyone outside of your little refine logic can just guess at what the name of this data is. You have to tell them by giving them this cryptographic reference. But the nice thing about the data lake is that it's very high throughput. Right? Across Jam, it's 2/3 of a gigabyte a second, right? That's for a blockchain system. That's pretty fast. Now, service storage, on the other hand, is slower. It's got maybe 1/10 of that throughput. And instead of being accessible in refine, service storage is only accessible in accumulate, later stage. But it has this great thing that it's got a namespace, and it's got a namespace that sort of gives you the ability to have keys as well as values. So you have a UUID service reference, which is your service, that's unique identifier, and then within your service's namespace, you can just call whatever you want, whatever. That's fine. And you can pass these cryptographic references from refine into accumulate, and that means that we now have a way of advertising data that we've put into the data lake in refine to people that are not not knowledgeable about what's happened in refine. We can pass them out and have them be stored in the service storage through accumulate. So, in essence, service storage is being used both to track the program state, the service's state, and it's also being used to give us clear references for data that we know is in the data lake because we know refine put it there. Good, right. On to picture of CoreVM. CoreVM, if you like, is kind of a Docker for Jam, right? Familiar with the idea of Docker? No? Yeah? So it's like a container, right? So you can stick executable code and data into a container and have it be executed in a very generic space, a space that you can count on environmental properties for. And this is the sort of thing it gives you. It gives you the red background arrows, not the blue background arrows. It gives you a regular virtual machine, a regular instruction set architecture, where memory is as you expect it to be, 32-byte addressable. And the arrows go all the way up and all the way down, indicating you don't need to be concerned about block gas limits, right? Or transaction gas limits, particularly. Now, there's still the bars between the arrows, right? We haven't made it like the ultimate possible compute system, but we have ways of passing data between the arrows, between these sort of everlasting processes, services. Actually, in CoreVM, they're called kind of inner VMs or guest programs. So yeah, CoreVM allows us to emulate a machine near x64 speed, native. RISC-V, the actual hardware ISA is RISC-V compatible. Page memory, continuous execution with message passing between instances. In essence, it can run normal software. So how does it work? Well, basically, it's like an initialization followed by a loop, an advancement loop. In the initialization, we zero out all the registers. We do what you would do on hardware, on regular computer hardware, right? On a normal computer. We zero the registers and the program counter. We empty the page table so there's no memory allocated. And we set what code it is that it's running. We don't put the code in the regular memory. Instead, we put it in some side memory that's like read-only. And so in this way, it is a Harvard architecture machine. And then in the advancement part, we advance the inner machine. We advance this sort of guest machine, just like you would do on, Parallels or whatever, virtual machine. And then we manage a few different sort of exceptional outcomes where, it's not just a basic instruction to be executed. One of them is the page fault. If there's a page fault, so if the program is trying to fetch something from RAM that isn't there for whatever reason, then we sort of provide the memory page from the data lake, if it exists. If it exists in our page table. If it doesn't exist in our page table, then we make a new page, all zeroed out, and put it in the page table. We don't do anything with the data lake yet, though, in that instance. If it's like a host call, so basically like this sort of, this irregular instruction that's doing something beyond the actual machine state, in this case, outputting some data, because that's generally what we want to be able to do, right? We want to be able to output data. Yeah? Then we timestamp the data, and we put the data itself in the data lake. We put a reference to it in the service state. And when the machine runs out of gas, then we snapshot all the pages into the data lake, and again, reference them in our service state. So specifically, 4 kilobyte guest RAM page contents go into the storage. The output of streaming virtual devices, frame buffers, audio frames, console output also go into the data lake storage. And in the service storage, the synchronously available storage, that's uniquely identifiable, one place, nameable, we put the commitment to the guest PVM, which includes the registers and the program counter. We put the full page table mapping that maps page index to hash, and the code hash. We also put time index device commitments, virtual device commitments. So for example, the virtual graphics card, we put commitments to the video frames that it's been outputting. For the virtual audio card, we put references, commitments to the audio frames it's been outputting. For the virtual console, we put references to the console text frames that it's been outputting. And we also keep a little bit of bookkeeping as well, like who owns the service, who can upgrade the code. We need a few tools for this to work. One of them is the CoreVM player. This is like a monitor. Now, this can run on any machine that has a node on it, that has access to a node for the jam. And what it does is it monitors, you can point it at a service, a CoreVM service, and it will monitor the output streams of that service, looking out for time-stamped video frames, audio frames, console output, and it will just basically put it out on the screen. It's just literally a monitor for a CoreVM instance. We also need a sequencer, basically, builder, a work package builder, that understands what's going on in the CoreVM to some extent, understands which memory pages it's going to need, and basically kind of references them in advance, so that when the work gets into jam, they don't have to figure it out on the fly, because that's kind of slow. So now I am going to show you, hopefully, a demo of this. This is a new laptop. I bought it yesterday when I realized I hadn't brought the laptop that it's actually installed on. So I am hoping this is going to work. Okay. Right, let's see if I can move this over a bit at a time. this is horrible. Right, so we've got jam top running there. You can see that. And, is there some way I can not have to do this? Let's see, maybe I can set this up so mirror, that might work. Apply, fingers crossed. Scale is pretty crazy. Let's keep the changes. Maybe we can change the scale to something sensible, like 100. Apply. Keep changes. All right, this looks about right. So, yeah, we have jam top. There it sits. We actually have the testnet already running, and hopefully this is going to work. Then we have a few different windows. The first one that I'm going to start basically just sets up the virtual file system because the program that we're going to run needs a file system. So this basically creates a sort of hard disk inside of jam. Once that's done, it's going to upload the data into jam. It's quite a lot of data. It's like 4 megabytes or something. And we'll see, maybe if I extend this, we should see the data that that the jam bootstrap service is storing go up. And that's the struz and struz. But maybe it's, yeah, okay. So it's vaguely going up. And then we'll also see as the data is provided, it says sort of one provision, one prov, the bottom right of that top left text chunk. 4M, which means 4 megabytes, has been provided in that block. All right, good. And now that's finished. It's provided 6 pre-images. Next, we are going to create our virtual machine, passing it the code of the program that we want to create. There we go. Now, that's gonna do its thing. First uploading the code, and then creating the VM with the code. We'll need to do 2 other things once that's done. One of them is start the builder that builds the packages, that sort of move this thing along, tick it along, advance it. And the other one is the player, which monitors the output on the blockchain. There we go. So that's been created. And the service is this 32-bit sort of, not hash, but like pretty arbitrary code, arbitrary value. And we can see it's been created, sitting there. Now it's not doing anything yet because we haven't started the builder. We have to start the builder here. But before we can start the builder, we have to point it at a service because there might be lots of them. So I'm going to put the service ID in there, and then network is unreachable. Right, let's connect to some random Wi-Fi. It doesn't actually need the internet, but I will need to provide it some sort of networking. Can I get my little bag, the other one? Yeah, great. I'm just going to quickly tether it. I think it's already got the password, so it should just work. Personal hotspot is on, black iPhone. Connect. Oh, it's connected. All right, good. Let's see. Try that again. And there we go. So it's now found the service. It's figured out the code's stored there, and it's now starting to build packages. So let's start the player. And there's that. And this, what it's doing now is it's running the program, as you can see, in the jam top. It's running this program running in the VMs, as you can see with the orange blobs. But it's not yet created enough that it's properly sort of buffered. So it waits until it's buffered, I don't know, like 15, 18 seconds worth, so that in case there's like, you know, a network outage or something, it's still going to be able to play a little bit. And there we go. So this game is Quake. It came out mid-90s. It's It's a bit different. It's got a few different sort of things to what I've demoed in the past, Doom, which I'll talk about in a second, but I'll let you sort of watch this. Now you can see at the top right there, the jam is sort of going fairly continuously. It's not maxing out its cores. It's using maybe half of them. That's about 50% there, I guess. And we're switching between the first and second core, mostly just to demonstrate that it's stateless. It doesn't need to sit on a single core. Yeah? In reality, it would just depend on which core or cores you've purchased as the work package builder, like which ones you can access. This will play through, pretty much indefinitely, but I've got to wrap up pretty soon, so I will move back over to the laptop. Yes, good. All right, so I just want to quickly talk about how we sort of did this. Going from Doom to Quake, there's a few things that we had to do that we could get away without doing on Doom, because it's just a simpler game. So the first thing that we did for Quake was we ported Muzzle to run on, PVM, compile for PVM. That was relatively straightforward. And then also the sort of jam environment that PVM, that run PVM, the PVM ISA sort of sits under. That took a bit longer, but not too long. We had to we couldn't skimp on the memory manager, so the thing that's picking the memory pages. It turns out that Doom uses about 134K memory pages, and they're just the same 134K memory pages more or less throughout. So if you only ever just put in the memory pages that were last written to or last accessed, you'll be fine for, I don't know, 10 minutes or something of demo play. You can't do that with Quake. It actually flits around the memory quite a lot. So you have to actually work out which pages it's going to use before creating, in order to create a package that isn't going to stall. Finally, the thing that probably took the longest was creating this virtual hard disk. Quake actually requires a file system. So it stores a bunch of data in files, and the program itself expects there to be a file system that it can access through Muzzle or whatever in order to read from those files, potentially write to those files. Yeah, that took a little bit of work, but not too long. So status of CoreVM at the moment is that it has Muzzle support. So basically, if you have code that just requires libc, you can compile it directly for jam. That's fine. And it's got video output, audio output, terminal output. I didn't hear the audio, but this laptop, I couldn't get the speakers working, so it might just be that there's a bad driver for the sound card. The terminal output, you could see, I don't know if you noticed, but you could see at the bottom, it was like saying, rockets, 4 rockets, and all this sort of thing. And we have disk storage now. Things that we're working on the keyboard input, so you can actually make some input into the game or into whatever's running on the thing, and service interrupt, so you kind of get a virtual local area network. Good. I don't know if there's time for discussion, but that's the talk. Thank you very much for your attention.